try to teach a computer how to play Pac-Man via a microphone. And to give you a little preview of what we're going to be doing, I'm sharing this this website developed by Google, where you can play Pac-Man using a webcam. So we're gonna take this and we're gonna, modify a little bit, and we're gonna just try doing the same thing with a microphone. But to give you a demo of how that looks, so this is a Pac-Man that you can play with your webcam, so essentially with your face. So the first thing you need to do is to teach computer the commands that you want it to use. So we're using a webcam, so we obviously need 4 commands. We need to go left, right, up, and down. So I'm gonna need to show the computer what the webcam looks like when I want to go left, right, up, and down. So let's start with the up. So I guess if we want to go up, let me do this, and I'm gonna add a couple of examples of this is what I look like if I want to go up in the Pac-Man. Let's do the same for the down. So this is me going down. Let's do left. Great. And then let's do right. I'm moving a little bit just to give the computer a better idea of what it means to do left and right. And once I've collected enough samples, so I think I have around, I don't know if you can see that, I have around 30 frames for each command. I can click training model, which will take the samples I've collected, and it will train the neural network, which you can see at the top, to prepare the neural network so that I can play the game. Now everything should be ready. So if I do play, ready. Okay, let's go. Left, up, left, down, left, up, right. Come on. Oh no, I went like, oh, okay, I died. However, you can see that works pretty well, and it was super quick to teach the computer what is it that we want to do. So that's what we're going to be doing in the coding part. In the second section of the workshop, we'll just modify it, and we're going to be using a voice command. So you will need a microphone for that. All right. So that's a preview of what we will try to achieve. And if I go back to the presentation, now what we're going to do for about 20 minutes is just going through some intro about what machine learning is and why you might want to use it. All right, so machine learning is a new way of programming computers, essentially. It's not very new, but I felt it sounded better, if I said that it's new, because everything new is obviously much better than everything old. So in the old boring way, the way we would program computers, if you wanted a computer to cook you a meal, for instance, is that you give it a bunch of ingredients, then you give it a recipe, which is essentially a step-by-step algorithm how to turn the ingredients into a finished meal. So this is a traditional way of how you write code, and that's how most of us write code every single day. So we tell computers step by step what is it that we want it to do. The problem with this old way is that it's very time-consuming and tedious. Computers are really stupid. They don't really know anything about anything, so you have to be extremely specific, and which takes time. And also the other problem is that you need to know the recipe, and you need to be able to describe it in a step-by-step form, which might not always be possible. A traditional example of that is a spam. So if you look at this message, it's written in English, it's using real world words, but if I read it, it's immediately obvious that there's something dodgy about it, and it's probably not a genuine message. However, it'd be very difficult to describe to the computer how I can tell that. I just know from some of the words and the context and the wording. It's very difficult to come up with that step-by-step process. Which is why we have the exciting new way, machine learning, in which case we give a computer the set of ingredients and we provide a lot of examples of the finished product. In this case, I think it's stuffed zucchini. And we let the computer figure out how to get from the ingredients to the finished meal. So we don't have to provide that step-by-step recipe. A great thing about this is that we can teach computer more complex tasks because we don't have to provide that step-by-step list. It means that we can do more difficult things that will be very hard to describe just if you were to sit down and write it on a paper. And also we can let the computer learn things that we don't know about. So that's a case of letting the computer figure out connections that we might actually not be aware of, at least not consciously. Obviously, nothing's perfect. So there are some problems with the new way. One of them is that you need lots and lots of data. So in case of the meal, you need to provide a lot of examples of ingredients. So because you don't want the computer to get confused about having a slightly different shape of a tomato, for instance. So you need to provide a lot of examples of tomatoes of different size and colors for the computer to understand the essence of a tomato. The second problem is that you won't know what the recipe is. And if the computer decides to start adding polonium into your recipe, into your meal, you might not know because it functions as sort of a black box. Which brings us to the good thing about the old way, which was that it's transparent. So you can always review the code and see what it's doing. And it's accountable. Someone wrote that code and you can, go to them and ask them, why did you do this? You need to fix it because it's broken. So how do you know that your problem is a good candidate for machine learning? And there are, generally speaking, there are 4 rules that you can use to see if you should even attempt to use machine learning to solve your problem, because it's tailored for certain kind of tasks. And I'm going to explain these rules on everyone's favorite example, which is a self-driving car. Rule number 1, a human expert could perform the task in a few seconds. So at this stage of where we are with machine learning, it is really about automating very simple tasks. And it is really about automating something that we can do very quickly without too much cognitive effort. It can still be a very complex thing, but we can just do it almost automatically. With the example of driving a car, once you've learned to drive a car, you can do it while having a conversation with your friend or listening to music or something. But you are still doing quite a lot of things at the same time. Number 2, it's difficult or impossible to write down the rules. So that goes back to the original example. If you think about driving a car, there's just too many scenarios and too many edge cases, and you'd never be able to write a fully comprehensive list of all the if statements for the car to know what it needs to do in every possible situation that might occur on the road. Number 3, it's easy to get examples of desired behavior, which goes back to the idea that you need a lot of data. So to be able to solve problem with machine learning, you're going to need to be able to find or collect lots and lots of data. Ideally, with the example of self-driving car, it's very easy to have a human driving the car and then just record everything they're doing. And you can do it, as much as you want, and it's easy to collect a lot of high quality data. So essentially you can observe people doing the task and do the data collection. And number 4, knowing the rules would enable actions to be taken. In other words, this means, do you have a problem that's worth solving? Again, machine learning is a tool. So if you you might need to think about, is there a problem that you're really trying to solve, or is it actually not a problem, or maybe you're just looking for a solution without having a problem. Again, the example of self-driving cars, you know, it's a worthy endeavor. We might want to have cars automated, just because people, you know, make mistakes when they drive cars. There are a couple of key components of machine learning systems. One of them is an algorithm that's being used to train the model. The other one is data, which gives the algorithm examples of the real world scenarios. And when you combine the two, you end up with a model. It's important to think about these different components, because a lot of times, you know, there are obviously a lot of discussions about bias in AI and machine learning. And a lot of sometimes people say, you know, it can't be biased because it's algorithm, and algorithm is essentially, you know, mathematics or just a code. However, algorithm is just one part of the machine learning system, and there's also data that's collected by people in a real world, and that's where the bias comes from. Another thing to consider is that the algorithms you're going to be working with, you might not really understand how they're working, and they've been probably developed by some smart people at some university, probably either in the US or in China. And then the data you're going to be using for training your model has been probably collected by some big company, again, probably from the US or China. And then the models these are used by everyone else. So again, it's important to consider that all these tools that we're using have been created by certain people, and they fit certain, you know, certain edge cases and certain scenarios. So it doesn't mean that they are always the best for no matter what you're doing. There are different kinds of machine learning. One we're going to be doing today is supervised learning. The other one is unsupervised learning, and then we have reinforcement learning. So if we start with the first one, supervised learning, in this case, you tell the computer what the correct answer is. Going back to the example of the spam, with supervised learning, you give computer a lot of examples of email messages, and you tell it, this is a spam, this is a genuine message, leaving the computer to figure out the relationship, how to get from the sample to the correct answer. The demo I've done at the beginning is an example of the supervised learning as well. And supervised learning is traditionally used for predictions, when based on no data, the machine learning will predict unknown outcomes, which can be used, you know, for forecasting sales or medical risks. A popular toy example of that is predicting who's going to survive on Titanic. So there's a well-known data set that lists all the passengers on Titanic, and what supervised learning is used for is to figure out the relationship based on all the attributes we have for each passenger, which could be as you can see in the table, which could be their name, their sex, their age, the kind of ticket they had, you know, which class on the ship they were in. So it takes all these parameters and tries to predict, you know, if that person is going to survive or not. And obviously there are no spoilers here. The secret to surviving on Titanic is being rich and being a woman. Another example is predicting if a Instagram account is a genuine account or it has been created by a bot or some automated process, in which case we look at things like number of posts, number of followers, is a profile photo, and we try to work out, is this a genuine profile or not? So this looks like a genuine profile. That's my profile. So it has a profile pic. It has some ratio between followers following. There's a bio, there's a link, comparing to a fake profile where it doesn't really have that much information, which could be a signal that it's not a real profile. And if you wanted to see how to do this fake Instagram profile detection with JavaScript, there is a repo that you can check out the code how to do it in TensorFlow.js, which will be the library for machine learning in JavaScript that we're going to be using today as well for something else. I'll have this link at my very last slide. A second example is unsupervised learning, where you don't tell the computer what the correct answer is. And this is popularly used for finding hidden patterns in the data and finding similarities in data. One of the examples is this wonderful project by Google called Bird Sounds, where they look at audio snippets of different kinds of birds, and they had an unsupervised machine learning process clustering them so that you can end up with this little visualization where you have, is this gonna work? Oh, it's loading. Where you have audio snippets of different kinds of birds. And let's see if this loads. And you see that similar types of birds end up in a similar part of this visualization because they sound very similar. So here we have kind of high pitch tweets, I suppose, where you can go to a different spectrum where you have much, oh, that's much deeper sounding birds. So again, it might be very difficult for a person to, try to find similarities and group these audio snippets together. But with unsupervised learning, you can have the computer to look at it and find patterns, which is again example of sometimes the computer trying to figure out a relationship that we might not be aware of. Cool. The last one is reinforcement learning, where you don't tell the computer what the correct answer is, but you reward it if it gets it right. So this is traditionally used for tasks where you have some sort of score. The video I'm going to show you is a research project where they took a human-shaped body and they put it into a physics engine, and they told the computer to try to maximize the distance the body would travel. The body has joints and everything, so it reasonably resembles human body, but they didn't tell computer anything about how we move as human, and they let the computer to figure out what's the most efficient way to move these set of joints and muscles to maximize the distance traveled. And this is what it ended up looking like. Right. So as you can see, quite a funny movement, which comes from the idea that computer knows nothing about what it means to move like a human, so it tries to figure it out on its own. Another very famous example of that is AlphaGo, where a deep mind, I believe, let computer play the game Go, and it didn't tell it anything about the rules. It just let it play against. I think they started with playing against humans, and then the system started to playing it against each other, teaching itself what it means to get really good at Go. Again, there were no rules. They didn't specify anything about the game. They just the computer knew where it lost and when it won. And one more example of that is someone actually trained the offline Google Chrome dinosaur game, again using reinforcement learning. So the computer just tried to play the game again and again and again, pressing the space bar at random moments, trying to teach itself how to get further in the game and how to get the highest score possible. There's a fourth bonus type, which is my favorite, which is also using humans to do the work, which is actually how a lot of the voice assistant software started, where they didn't have an idea, they didn't have enough data to train their system, and they didn't have the idea also what people will be asking, what kind of questions, which is why at the beginning, Siri, Alexa, and a lot of these systems, there were actually a lot of humans on the other end of the line, listening to what people are asking and trying to understand how well people use this product, and also collecting the data of different people asking questions, in different way, in different accents, with different level of English and all that. An example is a project using humans to do sort of an AI type work is a selfie city, which is a really nice project looking at analyzing different selfies taken on Instagram from different cities. Right. Why should you do a machine learning in JavaScript? JavaScript isn't a language that's commonly used for machine learning. Sometimes people react a bit funny when you say that you can do that, because languages like Python are way more common when it comes to sorry when it comes to machine learning. And people usually mention 4 different reasons. So let's go through them. One is that all you need is a web browser. So meaning there are no installs, there are no drivers, and it's going to work across all devices. Which, if you think, is actually quite a lot of devices. Obviously, it isn't just your laptop or your computer and your mobile phone. It can be also your TV, your fridge, your car, probably your door as well in the near future. So it's actually a lot of devices. Using JavaScript in a web browser means that you can do machine learning across all of these devices, and you don't have to worry about platform specific issues. As long as you can run a modern browser on the device, you can use machine learning and in JavaScript. Another reason is obviously JavaScript handles user input really well, because it's JavaScript is a king of the user interaction. So it's really handy for providing UX feedback and client-side validation. Most machine learning projects are not done in isolation. So there is a chance that you're going to need some sort of user input, and that's where JavaScript really shines. Another reason is keep it private, which means that if you're using machine learning in web browser, all the data stays on the user's device, meaning there's no sensitive data sent to your servers, which is obviously great for users, but it also saves you a lot of headaches of storing the sensitive data and worrying about which countries it's stored in, who you might be required to give access to, what happens when your database gets leaked, and all that. And of course, not having this to stream all the user data to servers It's also a nice little benefit of reducing the amount of traffic between a client and a server. And with all these devices, using and fine-tuning models in the browser actually means that you kind of have a neat version of a distributed computing and using, users' machine power to do machine learning as opposed to your server. A fourth reason, which is personally the most important for me, is that having machine learning available in a language that's as popular as JavaScript means that it makes it more accessible. So there is a hope that with machine learning in JavaScript, there could be a process of democratization and demystification of machine learning, and we should be able to give it the tools to as many people as possible. Okay, we are almost at the end of the presentation. I wanted to end with giving you a real world example of how I've used machine learning in JavaScript in Node, which was for the project called Reimagine the Game. And you can visit it at reimaginethegame.economist.com. Again, I will post the link. And for this project, we've looked at a football game from a slightly different perspective. And we wanted to tell the story of the football game with not what's happening on the pitch, but with what's happening in the crowds at the stadium. And we've recorded audio at the Allianz Arena, which is a home stadium of Bayern Munich, German football team. And then we've visualized it to give a different view of the game and of the key moments of the game. And I will show you an example of what that looked like. Right. So as you can see, it was a moment in the match where the two sides of the stadium kind of performed this oriented chant. The source data we had was in the format of a heat map video. So let me play that for you. So on this heat map video, as you can see, the color signals how loud it is at that particular moment, at that particular point, at that particular place at the stadium. So the purplish means very loud, the greenish means less loud, or blue. I don't think we have any blue. So you see that there was obviously the same example of the two sides of the stadium. And if I play it again, if you're gonna pay attention to the right-hand side where the scale is, you might spot immediately an issue that we had with the data. Let me play that. Sorry. So this is what the scale looked like, and you can probably tell that the problem is that we don't have a fixed scale, so it's dynamic, meaning the meaning of the color actually changes across frames, and the same color can mean different values of volume depending on the value of the dynamic scale. We didn't really have any other data connected to this video, so the video was all we had, which meant that we had to figure out a way how to read these numbers from the video to be able to translate the values, the color into actual absolute values of decibels. So how loud it was, meaning we had to work out how to read this number, and none of the commercial solutions available worked. So we actually had to train our own model using transfer learning, which is something we're going to be doing today as well. And with transfer learning, you take an existing model, in this case, a labeled data set of a lot of images, and you retrain it using your own data. In our case, it is these these individual digits. The video is computer generated, so you'd think it'd be pretty simple because all the digits should theoretically be the same. The problem is that they were so small that the digits started to bleed into each other. So 5 would look very different if it was next to 7 or 8, which is why we had to use machine learning to deal with that, uncertainty and to deal with that variability in the data. And these are the results we got. So you can see the zoomed in version of the video with the number, and then in orange is our prediction of our model. So you can see that works really great. And we needed just like 10 or 20 images to be able to do that. If you wanted to have a look how that's working, again, there's a different repo where you can have a look. This is an incorrect link, so I'll make sure to, that's the old link, so I'll make sure to post the correct one on Slack and in Zoom chat in the meantime. Okay, great. So this is end of the presentation. So we're going to be using a project called Teachable Machine, developed by Google. So if I go to this project, so it's teachablemachine.withgoogle.com. And when it loads, what you need to do is you need to go to get started. And on this page, you're going to select an audio project because we want to do a voice control of Pacman. So we're going to choose audio project. If we have time, we might do some other projects in the end, but let's see how it goes. So Teachable Machine with Google.com, you click, let me go back. You click get started, and then you click audio project. And you should see an interface like this that will allow you to collect audio samples from your microphone. Because we're gonna do voice control, unfortunately, I'll have to, there will be a problem if I kept talking because that would keep confusing your computer. So what I'll do is that I'll show you a snippet how to do it. So on this link, we will start with collecting samples for the background noise. So that is to teach the computer what it sounds like where you're actually not saying anything. You need to collect these samples because there actually might be a lot of background noise that you don't realize. Like I have a busy road outside of my house, outside of my building. So for instance, in my background noise, there's definitely going to be cars passing, and the computer needs to know this so that it can distinguish between your commands and then the background noise. So in the first section, background noise, I'm going to click mic. And I have a different microphones here, so I'll just choose a microphone that I'm using. You might not have this drop down. And then I'm going to record a sample. On the right, you can see that it requires 20 samples minimum. What that means is that it requires 20-second audio that will be chopped into 1-second pieces. So I'll click on the button at the bottom. It says record 20 seconds. It might say something for you, something different. So if you wanted to change the duration, you just click the little clock icon, and then you could change the duration because you're gonna need 20 seconds for the audio sample. Okay, so the best part of the workshop, I'm gonna record background noise, meaning I'm not gonna say anything for 20 seconds. All right, great. So we've collected 20 seconds of an audio, and then we can click extract sample, which will chop the audio into 1-second pieces, and we have 20 of them. And I don't know if you could hear it, but there was definitely cars passing outside. There is definitely some background noise in my flat at the moment. So with the background noise covered, what we're gonna do is that we're gonna record samples for each command. So we're gonna have up, down, left, and right. So we're gonna need to collect samples of me saying up a couple of times and then me saying down a couple of times. It's gonna be a very similar process to collecting the background noise. So below the background noise, you have another box that just says class 2. So let me rename it to up. And again, clicking mic, and just selecting microphone in case you had more microphones connected to your computer. And now it asks for 8 minimum samples, meaning we need at least 8 seconds of audio of me saying up or you saying up. So again, with clicking the clock icon, you can adjust the duration. So I have a duration 10 seconds, so I can collect all the samples at once. So I'm gonna click record. Up, up, up. Great. We have 10 seconds of me saying up. I did try to change my the pitch a little bit and also moved a little bit so that the microphone gets slightly different samples. So it has a better variety of the possibilities of me saying up. We will repeat the same process for the other commands, so down, left, and right. However, you don't have to sit and listen to me saying this. So what I'm gonna do is that I will mute my microphone and finish training these, finish collecting the samples, and then we'll train the model and we'll explore the results and we'll see how people get along. So let's take. So as you can see, I've collected 3 more samples of me saying down, down, left, left, right, right. It was a lot of fun doing that. And once you have that, what you need to do is you need to click train model. And it's going to take a little bit of time. You have to stay in the browser because the browser is going to be training the model in meaning that if you switch to a different tab or something, the browser process will get killed. So you need to leave the browser open. It shouldn't hopefully take too much time. It should be 10, 20 seconds the most. And when you finish training the model, you're gonna get this new interface that is listening to your microphone, and it's gonna try to work out what you are saying. So as you can see right now, it's very confused because I'm saying a lot of words that it didn't hear and didn't have in the training data set, so it's trying to guess. But if I try to use some of the words that I trained, hopefully it should give us a good result. So let's see. Up, 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 left, left, right, right, down, down, and now we have background noise. So that seems to be working pretty good. Hopefully it works for you the same. There are a couple of more settings that for training the model that we don't really have to go into right now. So once you've tried it in the browser, it seems to be detecting the commands correctly. What you want to do is you want to click export model and click download, and then click download my model. And it should download a zip file. So again, once you've trained your model, you click export model, you switch to download, and you click download my model. There is also some snippet code that we actually going to be writing in the second section, so you don't have to worry about that for now. But once you downloaded the zip file, and if you unzip, you should see there should be 3 files, 2 JSON files, 1 binary file, and that's the train model we're going to be using in the second section of this workshop. So again, collect the audio samples, click train model, then export model, download, and download the zip file. And we're going to go to the coding part. So you're going to need code from the audio Pacman repo. So let me show you what that looks like. So you should have a couple of these files. You're not going to have node modules, so let me delete that. And that's going to be the first step. So we will need to install all the dependencies for the project, which is a typical for a modern JavaScript project, really. So if I go to my terminal here, you might have some sort of command line that's slightly different depending on your computer. on Mac, so that's what it looks like for me. So I am in the audio Pacman directory, which is the directory of the code. And what I need to do is I need to run, let me make that bigger for you, npm install. So first of all, you need to make sure that you have npm installed. So you can just type npm, and if you see this, that means that you're good to go. So if I'm gonna type npm install, it should download all the dependencies for the project. So that's gonna take a couple of seconds, probably. So we're gonna be using a build tool or bundler called Parcel. You might be familiar with Webpack or a similar build tool. So that's gonna be very similar to that. So once you've finished installing everything with npm install, you can run the project with npm run watch. So it is npm install and then npm run watch. That might take a bit of time, but you should get a message saying server running at localhost 1234. Wonderful address. So you're gonna go there. The first time it's gonna build everything. It's gonna take a bit of time, which is you see building index.js. But once that's done, every time we're gonna save the file, it's gonna hard reload everything, so it should be fairly quick. It's just the first compilation, I suppose you could call it. Takes a bit of time. So yeah, it was 1 minute in my case. It might be faster or slower for you. So yeah, after I've run npm run watch, I went to localhost 1234. And you can see a slightly different version of that website that we've seen at the very beginning. So that's a version. I took the example that Google made and I just modified it so that we could use models trained on teachable machines. Right, so if you can see this, that means that everything's working for you. And the next step will be to add the train model into the project folder. So you need to find that zip file that you've downloaded from Teachable Machines, which I think in my case it's in downloads. Yes, it is. And you will want to take these three files. So it's the binary file and the two JSON files. You're gonna copy them, and then if I go to the project folder, you will want to put them into dist. So that's a distribution folder. So you go to dist, and then you should create a folder called my_model, and then you should drop those three files there. So again, that's in dist, create a folder, my_model, and then drop the files there. You're free to call the folder whatever you want, but if you want to follow along, there's going to be less confusion if you call it my model. So let me post it to the chat as well. So I'm gonna open the project in my code editor, which is I'm using Visual Code. You can use whatever you want. It doesn't really matter for this project. To give you a quick overview of what we have there. So we have an index file that has all the markup as you'd expect. And then we have a UI.js file, which has all the controls for the UI. So you don't have to worry about this part. That's just there to make the game run and to have all the UI. So we're not going to be interacting with this code at all. That's just there in the background. And then the file we actually going to be using is the index.js. So that's going to be the file where we're going to be writing all the code. if you got lost or bored, or you just wanted to skip to the end, there's also index dash completed, which has all the code that we'll have in the end. So in case you wanted to, you got lost, something was not working, you can always check against that file. And again, in a dist, my_model is where you should have the files trained from Teachable Machine from that website. Cool. So if we start coding, you can see already that there's some code in place that is doing two things. One is it's initializing the UI, so that's going to load all the models and everything. And once you click the play button, it's going to start the game. And actually, by default, you can control the game. If you click play, you can control the game with just your keyboard. So you can always try that everything works as expected. But we're going to modify it so you can also control it using your microphone. All right, so let's get going. So what we're going to be using is a thing called speech command recognizer, which is a model that, or a JavaScript module that can be used to identify spoken commands. And you can either use it out of the box, or, which is what we're going to do, is that you can retrain it using your own data so that it works better for your scenario, because everyone has a slightly different voice. Your accent might be different from my accent, your microphone might be different from my microphone. So all these things come into play, and which is why you'll get the best results if you just use the model you've trained yourself, because it's trained with your own voice. So we already have in place the imported speech commands, which is the speech commands recognition model. And we're going to start in the init function. Maybe I could make it a little bigger, if that helps. I think that's going to be better. Yeah. And what we want to start with is that we want to create this new model. So you can start speech commands. And then if you look here at the example, speech commands model has a create method. That's what it is, method. So I type speech commands create, and then we have a couple of options, which you can see helpfully in this tooltip from VS Code, which you may get as well if you're using VS Code, or you might get something similar. And there are a couple of parameters that we need to set. The first one is an input type that's going to be used to transform the audio. There's really there are two options: browser FFT and soft FFT. We want to use the browser FFT because that's the FFT starts for Fourier transformation. So that's that's just a way to let browser handle the audio to simplify it, because audio is quite difficult to work with. So we let the browser and web audio API in the browser to simplify it for us. Another parameter would be vocabulary, which is which would be choosing if you wanted to use a particular set of commands. However, in our case, we actually are giving it a model, so we don't have to worry about it. So you can pass in undefined or null. And then last two parameters will be a path to your model. So you can see at the top, I've defined URL, which is pointing to the My Model directory. So the bundle tool we're using, it's by default serving everything from the dist folder, which is why we've added it to the dist folder. So again, that's here. So this is the path to the folder with our model. If you named the directory something else, you don't need to rename it here. And then we need to pass two paths. One is to the model JSON, and the other one will be to the metadata JSON. So let me do that. So I'll start with the URL, and then I'll just add model JSON. So that's a path to the model, and then path to the metadata file. So you should end up with something like this. So we're calling a create method on the speech commands and model module. Sorry, too many similar words. And we're passing in 4 parameters. So we're using browser, Fourier transformation. We're not using any vocabulary. And then these are the 2 files that we're going to be using for training the model. Once you've done that, there's one more thing that's good to do, which is to kind of warm up the model so that it performs better once you actually start saying things. And with that, we can do that with, So we've created the speech commands, and that will actually return the recognizer that we can use. So let me just define a variable here, and then whatever gets returned from the create method we store under the recognizer, because that's what we're going to be using in the play function later on, which is why I define it. Actually, let me define it at the top, which is why I define it outside of the function, so it's available both in init and play, so it's in scope for both of those functions. And one thing that we want to do that I mentioned is that we want to warm up the model before it gets used, so it's quicker once we start saying words. That we call a method on the recognizer, which is called ensure model load. It's asynchronous, so you might want to add wait in front of it. However, it shouldn't really make a difference in this case because we're not returning anything. And if you wanted to see what ensure model loaded is doing, let me find a documentation. And this says what I mentioned. So it makes sure that the model is downloaded correctly, and then it warms it up. So it prepares it for the use. So that's the init function. So we've created the recognizer model that we can use. And so let me actually just run that. So if you save that file, Parcel, our bundling tool should automatically reload it. So let's just make sure we don't have any errors. And if let me just log this out to see how long it's. If you got lost or you needed more explanation, you wanted me to go slowly or slow or more fast, just let me know in the chat. I can't see any of you really, so
no comments yet.
Okay, cool. In the index.html at the very bottom, just make sure that you're linking the correct file, which should be index.js. So at index.html, it should be index.js. I'm not sure if that might be the incorrect version in the repo. So it's linking the finish file. So yeah, just make sure that you're linking to the file we're actually working with, which is index.js. So if I reload this, yeah, now we can see that we can see our console messages. So we can see that it took a bit of time to warm up the model. Cool. This is the init method. So we're done with that. And the second part we need to implement is the actual playing of the game, which happens in the play function. So that is called whenever you call predict, which is this button right here, play, which will call a start pacman util function on that UI module that will just start the game and I haven't reprogrammed the game. It's just a code that Google has released. So that's linked right here. So you can also drop it and use it for something else. So yeah, so in the now all we need to do is just to implement the play function. That UI module has a method called move. So what we will want to do is we will want to call this method and pass it either left, right, up and down, or up and down as a string. So we'll want to pass it one of these. So what we need to do is that we need to listen to the microphone and then work out which word you've set so that we can call this this method move, which will move the character in the game. So that's how we're gonna implement the voice command. So let's start. So we have the recognizer, which contains the train model. And again, if I go to that README file again, you'll see that recognizer has a method called listen, which will listen to the microphone. So which is exactly what we want, because we want to react to you saying things to the microphone. Again, we get a helpful help from the VS Code hint pop-up, whatever, and in which you can see that there are two parameters for this listen method. One of them is a callback. So that will be a function that gets called every time the model detects you saying something. So we have a recognizer, which is containing the results of the trained model that we've done with the create method of speech commands. And then we have a listen method, and the first argument is the callback that you get every time you say something. So if I try that, let me go to, and if I click play, because that will call that play function, you see that it's picking up the big background noise, but I get constant callback whenever there is some activity on the microphone. So let's see. So obviously that's not very helpful. We need to find out what is it being set. So let's see what we get as a parameter for that callback. So the callback gets called with a parameter. I'm calling it result. You can call it anything you want. And again, if I click play, so this is what we're getting in that result object. And you see there's a couple of properties. We're going to be interested in one called scores. And if you look at it, it's an array of 5 items of 5 float numbers. And what these numbers are, they are probabilities of you saying one of the words that you use for training, which is why there's 5 of them. Because if you remember, during the training, we've trained 4 commands, and then there was a background noise. So that's 5 of them. So I will want to get that scores, result scores, result scores. Can't type. Great. And if you think about it, what we need to do is that we need to pick the one that has the highest probability, because that's probably the word that you set. So we actually don't care about any of them but the one that has the highest probability. So the way to do it, there's a couple of ways. I guess the easiest would be to find the maximum probability from the score. So if I say max prob, and then we can just do, it's an array of numbers, and we want to find the highest number in the array. So that's one way of doing it, using spread, so that it looks into the array, gives me the maximum number. Sometimes when you're too quick to hit play, you might get an error message or something. So you might need to wait a little more. And now we're getting numbers that are ranging from 0 to 1. So if you get something like 0.59%. It means 0.59. It means it's 59% probability that it was the word. Sometimes those probabilities are actually not that high. And we might choose that we don't want to react to it because we're not really certain what, what you've said. So to be able to fine tune it, what we can do is that we can use a second parameter of that listen method. So if I put a comma here, the pop-up should come up, which is config. And we can pass a couple of options for how we want to listen. Again, if I go to the documentation, there are a couple of methods. But the one we want is probability threshold. So let me type that here, probability. And what this allows us is to let the model know that we're not really interested in getting the results unless there is a certain certainty that we've said something that has been detected. So let me put in 0.75, which means 75% chance. What this does is that if if I'm gonna keep talking and I'm not gonna be saying up, left, down, or right, it might still get some results and it might still guess if I'm saying one of these things, because we've trained a model with just 5 of these examples. Everything the model listens to, it tries to work out which of those 5 things it is, because that's all it knows. Which is why it might get it wrong many of times when I'm saying just random words, and because it won't, then it will give us like very low probabilities of, oh, maybe it was up because I've said something that might sound like that. So we want to avoid that because we don't want to have the game just going completely at random when I'm saying things. So, which is why we're including probability threshold 0.75%, so that we know that there's certain certainty that you actually said the word. And we're getting very, very close. So now we know the maximum probability, and the next thing we want to know is which index in that array was that maximum probability. So we need to work out which class it was. So again, many different things are doing it. One way we can do it is we can look at that array and we can look for that maximum probability value. So that will tell us the position of the maximum probability in that array, and we are getting very, very close to the end, both in code and in time. So that seems to work out quite well. It seems like the hot reloading is not really working as I expected. So you just need to refresh every time you change the code. Okay, let's see. Left, up, up. You might not be able to see it very well, but it's giving me different indices. So it seems to be picking different items from the array, which seems good. One challenge that we'll need to do is we'll need to work out which item corresponds to which command. I think sometimes when you train the model, it doesn't really keep the order. So we'll need to make sure that we have the right order. So we want to call the UI move with one of these left, right, top, bottom. So essentially we need to map the numbers we're getting, the indices we're getting to these commands. So what I'm going to do is that I'll do some lookup map table where I say for each indices which command it is. Again, there are different ways of doing it, but this seems like the most straightforward. So what I need to do is that I need to do, if I say up, 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 it seems to give me index 4, meaning that that class is on the position in that array 4. So I'm going to type 4 as the key and then up as a value. And we're going to do this with the other ones as well. So if I say left, left. Okay, so it seems to be 2 for left, down, down, down. It seems to be 1 for down, meaning that it has to be, oh, actually we don't know that because that's background noise. which one? Yeah, right. So it's number 3. Cool. And okay, if I don't say anything, okay, yeah, I'm getting 0, so we can add in 0 for background for noise. And based on this, so we have the index and we have this map, so we can actually work out what is it that I'm saying. Into the map, and I want to use the max index to work out what is the command. So if I can console log it, click play. I don't know if you can really see my console that well, but when I say left, left, right, right, up, 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 down, it seems to be doing the right thing. So the very last thing is that we want to pass this command into the move method of that UI module, which will move the character in the game. One thing you might want to do is, because this move is expecting one of these 4 strings, you might want to check that you actually don't have the noise, because that wouldn't really do anything. So you don't have to call that method. So yeah, calling UI move method with the command, which should be one of these strings. And yeah, hopefully now it should work. Left, up, left, down, left, 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 up, right, up, down, down. Ugh. That seems to be working pretty well. Every time one of the moves is activated, it also highlights it in the UI, so you can tell if it's doing the right thing. So if I try again, right, up, right, oh, that was lucky. Down, left, right. Oh, all right. I have one more life, but so yeah, so that seems to be working pretty great. So that should be everything for this exercise, making a Pac-Man microphone controlled Pac-Man. So thank you for listening. Hopefully this was interesting enough.